I'm going to talk about a couple of things you probably know something about, one of them being El Nino and the Southern Oscillation, or ENSO, and the other being climate change. But I'll also tell you about some things you may not know about, which is how they affect one another. And so I'm going to cover 4 topics. I'm first going to give you a basic overview of ENSO and its dynamics, its properties, and its global consequences. I'll then say a few words of introductory comments about human-caused climate change. But then the rest of the presentation will be addressing two questions. One is, how does climate change affect ENSO? And the other is, how does ENSO affect climate change? So to begin, here's some cartoons that characterize the ENSO cycle, the cycle between warm events we refer to as El Nino and cold events we refer to as La Niña. ENSO is the strongest year-to-year climate fluctuation of the planet. It's a natural occurring variation. It's been happening for eons. It originates in the tropical Pacific through interactions between the ocean and the atmosphere that are controlled by changes in sea surface temperature and winds. And it's been a problem that has fascinated climate scientists for over 50 years, but it's also of great consequence because it affects the entire planet, as we'll see. Here will be a short illustration of how El Nino and La Niña develop. So we start with normal conditions. We typically have a high pressure system that sits over the cold water of the Eastern Pacific and a low pressure system that sits over the warm water of the Western Pacific. The air at the surface flows down this pressure gradient. This is the trade winds. And these trade winds pile up water that have been heated by the sun in the far Western Pacific. It creates what we call a warm pool of water. And then the Eastern Pacific, the thermocline, which is the sharp vertical temperature gradient region that separates the warm sunlit layer from the deep cold interior, that tilts up towards the east in response to the trade wind forcing. And through a process we call equatorial upwelling, it brings cold thermocline water to the surface, and it creates this cold patch of water that extends from the coast of South America all the way out to the international dateline. Now, over the warm surface water, heated air rises. And when it gets to the middle atmosphere, middle of the troposphere, it condenses and it rains out. And airflow returns aloft to the Eastern Pacific and sinks over the high pressure region of the Eastern Pacific. Now, every few years, the trade winds weaken. And when that happens, it allows the warm pool in the Western Pacific to migrate into the Central Pacific. So that leads to unusual warming here. And the thermocline flattens out, so it's harder to upwell water into the Eastern Pacific, so it warms up in the east. The clouds and rainfall form over the warmest water. So as the Central Pacific warms up, all those cloud bands and heavy rains from the Western Pacific migrate eastward. And there's an inflow of air towards these clouds. And so a weakening of the trade winds leads to warming, which leads to a further weakening of the trade winds, which leads to further warming. And the system becomes locked in a self-reinforcing feedback loop that allows these initial perturbations to grow. Now, after several months to a year or so, warm water leaks out of the equatorial band towards higher latitudes, and that causes the thermocline to rise. And it rises close enough to the surface that it reinitiates upwelling, and it may actually overshoot and produce such strong upwelling that we switch into a La Niña phase, where we have very strong trade winds, very cold water in the Eastern Pacific. The heavy rains and deep convection shift westward over Australia, Indonesia, and the Philippines. And so this is how El Nino and La Niña work together over one complete cycle. So we have several indices that we use to track El Nino and La Niña, and this is one. We call it the Niño 3.4 Sea Surface Temperature Index. It's a large areal deviation of it's a large aerial average of deviations from normal or anomalies in the Central Pacific, where the overlying atmosphere is particularly sensitive to changes in sea surface temperature. And this is a 40+ year record. It starts in January of 1980 and it goes to last month. And you can see these red peaks. These are the big El Niños of the last 40 years, and the blue troughs are La Niñas. And so the big El Niños were 82, 83, 97, 98, and 2015, 16. Now, there's a couple features about the ENSO cycle I want to illustrate here. One is irregularity. You can see that some of these events are stronger, some are weaker, some are shorter, some are longer. This is what we call ENSO irregularity. There's another feature, which is called ENSO asymmetry, and that is El Niños tend to be stronger as a group, but La Niñas tend to last longer. And you can see that pretty clearly in this time series. Some of the La Niñas, in fact, last 2 years, like here in 2010 to 2012. Some last 3 years, like in 98 to 2001. And this most recent 3-year La Niña from 2020 to 2023, and it just ended. There's another index we use called the Southern Oscillation. And this, the pattern shown here is a big seesaw in atmospheric pressure between the Eastern Hemisphere and the Western Hemisphere. It's called Southern because the centers of action are just south of the equator. This was discovered by a British meteorologist about 100 years ago who was trying to find a way to predict weather and the monsoons over India. Now you can make a time series or an index of this by taking air pressure at Tahiti and air pressure at Darwin, Australia, and making a difference. And that difference is shown here on the top panel. This is what we call the Southern Oscillation Index. It's basically a measure of the strength of the trade winds because the air, as I mentioned earlier, near the equator is flowing down the pressure gradient. So if Tahiti has higher pressure than Darwin, like shown here in blue, that means strong trade winds. If Tahiti has lower pressure than Darwin, it means weaker trade winds. And you can see the relationship between the Southern Oscillation Index and the Niño 3.4. They're almost perfectly anti-correlated. Strong trade winds go with cold temperatures, weak trade winds go with warm temperatures. And we call this coupling between the ocean and the atmosphere. It's what makes ENSO work. Now, I mentioned this most recent 3-year La Niña, and that's right at the end of this record. And I just want to show you what the features of this looked like in the third year, at the end of its third year. This is October, December 2022. It's the end of the triple dip La Niña, as we call it. And what you can see on the top left, this is very cold, unusually cold, warm water along the equator from the coast of South America out to near the international date line. That's accompanied by stronger trade winds. These vectors are pointing towards the west. That means the trades are stronger. Remember, these are anomalies. They're deviations from normal. So we have the normal trades, but they're even stronger than normal. The air aloft, this is at the level of the jet stream, high up in the atmosphere, is stronger to the east. And that's this return flow that I mentioned in the little cartoon. And so we have the stronger flow at the surface and a stronger flow above. And then associated with the cold temperatures in this stronger, atmospheric circulation is a shift in the rainfall patterns. This is very dry now in the Central Pacific, where the rains typically fall. And because it's cold there, the rains have shifted to the west over Australia, Indonesia, and the Philippines. So this is what La Niña looks like. If you wanted to think of El Niño, it would be basically the opposite sign of these sorts of anomalies. So what happens in the tropical Pacific doesn't stay in the tropical Pacific. The shifts in rainfall associated with underlying sea surface temperatures release heat into the atmosphere. And there's a tremendous amount of heat release from these shifting rain patterns. And these generate planetary scale waves in the atmosphere that radiate out into the northern hemisphere and into the southern hemisphere through what we call atmospheric teleconnections. And these teleconnections change the global circulation of the atmosphere and the storm tracks. And so it affects El Nino and La Nina affect patterns of weather variability worldwide as a consequence of these teleconnections. And here's the global fingerprint of El Nino and La Nina. El Nino and La Nina are typically best developed in the Northern Hemisphere winter season, December through February. And what these patterns represent are shifts in the probability for certain types of weather events, droughts, floods, heat waves, extreme storms. And if we look down at the bottom here, associated with La Nina, as I mentioned, all that heavy rainfall shifts from the Central Pacific to the Western Pacific. So it's usually very wet in Australia, Indonesia, and the Philippines, dry in the cold zone along the equator. In the US, it leads to drought in the southwestern US, in the desert Southwest, and where I live in the Pacific Northwest, it leads to wet and cool conditions during the winter. Well, did we see any of these patterns of weather variability during this 3-year La Nina? And in fact, we did. We saw 2 years of extraordinary rains in Australia, unprecedented rains because of this La Nina. On the Horn of Africa, we had a historic drought, which was threatening the lives of millions of people because of famine and crop failures. In the desert Southwest, the 2 largest reservoirs in the United States were drying up, Lake Mead and Lake Powell, because of the extraordinary drought and prolonged drought that this La Nina brought. And where I live, we had 2 successive winters of wet and cold conditions. So it does have impacts, and that's one of the reasons that we study it. We want to be able to understand, and we want to be able to predict these kinds of impacts that El Nino and La Nina have. So that's a brief overview of El Nino and La Nina. Now we'll talk about climate change. And I'm sure you've all heard about this, you know something about this, but I'll just review a few highlights. The first one is climate change is real. We have many indicators of it. On the right here is one of the most commonly used. It's the global mean surface temperatures, which have been rising over the past century. And the fifth IPCC assessment in 2014 noted that warming the climate system is unequivocal. There's no doubt about this. In fact, the last 10 years have been the warmest 10 years in the last 1,000 years. There are other indicators like melting Arctic sea ice, rising sea levels, and heat gain in the oceans. And we know the reasons for this. It's that humans are consuming fossil fuels and they're cutting down trees in the Amazon and the other major tropical rainforests. And this deforestation and the combustion of fossil fuels is raising heat, trapping greenhouse gases in the atmosphere. Carbon dioxide levels now are the highest they've been in 3.5 million years. They're 50%, the concentrations are 50% above pre-industrial levels, which were about 280 parts per million. Now it's about 415 parts per million. And the planet is likely to continue warming into the future. We have models that I'll show you in a moment that project forward in time for different scenarios. One is a business as usual scenario where society makes no effort to curb the consumption of greenhouse gases. And under that scenario, it's likely that global mean temperatures will rise by another 4 degrees Celsius by the end of the 21st century. If society takes the opposite route and tries to decarbonize energy systems and flatten the curve to hold warming down to 1.5 degrees Celsius above pre-industrial levels, we get this bottom curve here, which from the present, temperatures may rise only 1 degree Celsius or so. And there's another point about climate change that I want to make, in that it's dangerous. As we continue to heat the planet and it becomes more imbalanced in terms of its energy distribution, storms become more extreme, droughts become more extreme, sea level rise threatens to inundate coastal cities and threaten infrastructure that's been in place for tens to hundreds of years. So it is a serious concern. Okay, so that's a little bit of background on climate change. Now, one of the most compelling problems in Earth system science is how climate change affects ENSO, because as I mentioned, ENSO is the largest year-to-year climate fluctuation on the planet. It affects people, millions and millions of people, when a big El Nino or a prolonged La Nina occur. And so we want to know two things, really. Has climate change affected ENSO already? And if so, how? If not, how will climate change affect ENSO in the future? So let's look at some evidence to address this first question. Has climate change affected ENSO already? We have historical data. This is one of the longest. It's that Niño 3.4 sea surface temperature record I showed you earlier. But I just showed you the last 40 years or so, this period since 1980. Turns out, this is the satellite era for Earth observations. This is a very well sampled period. We know the ups and downs of this curve with high accuracy. If you go back further in time, we're less certain. And that's because before the 1980s, and even before that, the 1950s, we had to rely on merchant vessels taking volunteer measurements of sea surface temperature on their trade routes. And so you have a distribution pattern for these measurements going back in time that looks something like this. Lots of holes, some well-traveled routes, but lots of holes in the central eastern Pacific. So there's a lot of uncertainty. Now you could look at this record and say, it looks a little bit more energetic at the end of the record than before. But if you go back to the late 19th century, we know from historical accounts that there were some monster El Niños, probably as strong as there were in the late 20th and early 21st centuries. These are recorded in accounts of extreme drought in India and Northeast Brazil and in other parts of the world where we know El Niño has an impact. And so from these historical accounts, it's really hard to say with great certainty from this record of only 150 years that El Niño and El Niña have really changed. And so basically the conclusion here is this record is too short, really, for us to be confident that this last period is really different from the earlier periods. Now we can go back further in time for what we call proxies. And these are things like coral growth rings, tree rings, ice cores, lake sediments, and other kinds of indirect measurements of climate that encode something about temperature or precipitation. And these records, we can get hundreds and hundreds of years, going back thousands, in some cases, millions of years. And I'll just show you one example. These are coral growth rings from the Central Pacific and from 3 islands in the Central Pacific. And what the authors have done is the coral growth rings encode oxygen isotope information, which is a proxy for ocean temperatures. And so you can see, excuse me, the Niño 3.4 is the black line here. And then the coral growth ring records from 3 islands are shown in the different colors. And these have been filtered to focus just on the ENSO cycle. So it's a filtering between periods of 3 to 7 years. You can see there's a lot of correspondence between these in the last century. And so you might think, well, we could extend these records back in time if we can find fossil corals and use them. And so you can go back thousands of years and you find that, the period 4 to 7,000 years ago, ENSO cycle looks somewhat weaker than it does today. And these authors interpreted that as ENSO extremes of the last 50 years are significantly stronger than pre-industrial and maybe a signature of climate change impacts. But we have to be careful because there are other explanations for this. One is that the Earth's orbit around the sun was different. And the orbital variations, some think, may have actually caused the ENSO cycle to be weaker back then than today. So then the difference in that case would be interpreted as due to natural variability, due to orbital variations rather than greenhouse gas concentrations. And the other is proxies, regardless of which they are limited in their spatial distribution. So it's difficult to know exactly whether we've got the right sampling in space to put together a coherent picture of how ENSO behaved many thousands or millions of years ago. And then finally, these are proxies. They are only a indirect measurement of temperature or precipitation related to physical climate variability. It may be contaminated by chemical, biological, and other factors associated with, the physiology of a coral. So there's uncertainty there. So in answer to the question, has climate change affected ENSO already? Maybe. The instrumental record and the paleo proxies are suggestive, but the instrumental record is too short, and the paleo proxies have their own problems with interpretation. What about the future? For this, we have to rely on these big climate change models. And they have a long history of use in climate science, 50 years or more. And they have progressively improved over time. They're comprehensive. They have complete oceans and atmospheres, land systems. They include ice on the continents and on the ice caps. And some of them are Earth system models. They include information about the biosphere, plants and animals on land and in the ocean. The physical part of these models are based on fundamental principles, how air and water move in response to various forcings, and how radiation is transferred through the atmosphere. So they have a lot of advantages, but they do have limitations. You have to solve millions of equations on a grid that covers the Earth, and the grid cells are sometimes only 1 to 200 kilometers spaced apart. So, I mean, there's a lot that goes on scales of smaller than 1 to 200 kilometers of these models. And so for those processes like ocean mixing, turbulent mixing, or cloud microphysics, you need a formula or a recipe that says how those processes will change with in regard to the larger scale resolved variability. So these parameterized physics are often very crude, and that can lead to systematic error in the models, where they are consistently inaccurate in terms of their representation of something like sea surface temperature or wind. So like with proxies, we have to be cautious in our interpretation. Now, some of these models, we've had various, as I say, generations of these models. This shows the result of how ENSO behaved in models used in the 4th IPCC assessment in 2007. There's about 15 models here. And the question is, how does the amplitude of the ENSO cycle in 2050 to 2100 compare to 1951 to 2000? And some of these models show a larger amplitude, and some of them show a smaller amplitude. So the results are conflicting. Even if you take the best models, the ones that best represent El Nino and La Nina, those are the red, the deep red colors. Some of them show stronger ENSO cycle, some show weaker. So for a long time, you know, we were kind of scratching our heads. We really don't know. But now these models, as generations have gone on, have improved. And the models used in the most recent IPCC, Intergovernmental Panel on Climate Change Assessment in 2021, show much more consistent results. 38 of 43 models, or nearly 90%, show the ENSO amplitude increasing by 10 to 20% on average in the business as usual or high emission scenario by the end of the 21st century. So that's really good consistency. Now, and we can analyze these models, and we can determine what it is about them that produces a stronger ENSO cycle. And there are two aspects of the models. The first one is the characteristics of ENSO, the properties of ENSO, and the dynamics of ENSO depend on the background conditions on which they develop. And so over the course of the 21st century, it's expected that we'll see a warming all the way across the tropical Pacific. This is a trend in the background conditions, with a stronger warming in the equatorial eastern Pacific. This stronger warming means that the coupling between the ocean and the atmosphere strengthens. So a smaller change in sea surface temperature will produce a larger change in winds. So we have a stronger coupling in these models by the end of the 21st century. And the other aspect is upwelling becomes more efficient. And that's because warming at the surface will be stronger than the warming below the surface in the thermocline. So the thermocline intensity increases, and it makes a smaller vertical velocity more effective at changing sea surface temperature. So we understand the physics of why these models will produce a higher ENSO cycle or stronger ENSO cycle. Okay, well, like with everything, there's a caveat. Here's that trend that the models produce over the course of the 21st century. This is the trend in sea surface temperature and winds. What is the observed trend? Well, that's up here. The observed trend actually is one towards cooling in the Eastern Pacific. Doesn't look like this. And in fact, if you ask these models, what would we expect of the sea surface and wind trends for the same time period that we observe this trend in data, it says warming. Now, if these models are to be believed, then we would argue that this trend is a form of natural variability. It's happening naturally, and that with time, it will be overwhelmed by the forced warming that we see here. Now, this background state, warm background state, produces a stronger ENSO cycle. Not all models actually produce a warmer background state. A few, remember, it was only 90% of the models that produced this kind of warming and a stronger ENSO cycle. There are a few models that actually produce this kind of a background state. And those models, some people argue, are the ones that we should be paying attention to, because some argue they have better physical representation of ENSO. And then these models with the La Niña-like background state, the ENSO cycle is weaker. So we're again left with this fundamental uncertainty: is how will the background state in the tropical Pacific evolve? Because that's going to determine whether we get a stronger ENSO cycle, like most of the models are saying, or maybe a weaker one, like some of the models are saying. Okay, so another topic I want to cover is how will climate change affect, so yes, to summarize this, how will climate change affect ENSO in the future? ENSO amplitude may increase due to stronger atmosphere-ocean coupling and stronger upwelling effects on sea surface temperature, assuming that the background conditions become warmer in the Eastern Pacific. And this is a big caveat. One of the big questions now in the research community is how will the background change? The next question I want to address is how will climate change affect ENSO impacts? We've talked about how climate change will affect ENSO properties, its amplitude, excuse me, and its dynamics. For example, the coupling between the ocean and the atmosphere and upwelling processes. But what about the impacts? What about the teleconnections? And I'm going to make the point here that even though there's a lot of uncertainty as to how climate change will affect ENSO properties and dynamics, we can see already that climate change is affecting ENSO impacts. And in fact, we see the combined effects of ENSO and climate change are contributing to some unprecedented high impact extreme events even today. I showed you this picture earlier, this slide earlier, of some of the impacts of the recent triple dip or 3-year La Nina. What I didn't mention, but I'm going to tell you now, is that climate change is amplifying these impacts. And it's very easy to understand. In a warmer world, the atmosphere can hold more moisture. For every degree Celsius rise in global atmospheric temperatures, the atmosphere can hold 7% more moisture. And so where it would normally rain because of a La Nina event or an El Nino event, it's going to rain harder. So it makes strong rain events into extreme rain events, like we saw in Australia, or like we saw in Pakistan in the summer of 2022. This is the summer monsoon. We expect a stronger summer monsoon during La Nina events, and this summer monsoon was supercharged. In fact, you see the headline here: climate extremes, how global warming and La Nina fueled disasters on top of disasters. This is the amplifying effect of climate change on ENSO. Now, I mentioned the stronger rainfalls, but the same with drought. Warming temperatures causes land surface, excuse me, to dry out more. And so if you have a drying trend and then you superimpose a additional drying and trend due to La Nina, you can have extreme drought. This was the case in the Western US these past few years, where the slow warming, global warming, has produced a slow trend towards drying in the West. And then we had 3 years of extreme drought because of the exceptionally long La Nina. So even without being certain about how the dynamics and the properties of ENSO may change, we can see now that its impacts are being amplified by climate change. Okay, the last topic that I want to cover is how ENSO affects global change, global climate change. And it doesn't so much affect the dynamics of global climate change, but it does affect our ability to cleanly detect it. And here I'm showing you, this is our friend on the bottom, the Niño 3.4 sea surface temperature index over the past 40 years. And there's our recent triple dip La Nina. The top here shows the trace, the monthly, these are monthly values of global mean surface temperature, that's GMST, from 1980 to the present. And you can see there's the rise in global mean temperatures. You can see lots of ups and downs as well. And why are those ups and downs there? They're there because of El Nino and La Nina. You can see that during an El Nino, global mean temperatures rise, and during La Nina, they fall. And you can do a statistical analysis, and you can see for every 1 degree Celsius change in Niño 3.4, global mean surface temperatures rise or fall on average by about 0.07 degrees Celsius. And there's a lag of about 3 months because the heating from the ocean during El Nino has to be distributed throughout the globe. Now, why is it that El Nino and La Nina redistribute heat around the globe on this year-to-year time scale? It's very easy to understand. You know, during El Nino, the ocean surface warms up all across the Pacific. There's more evaporation from the sea surface. And when that moist air condenses in the atmosphere, it releases heat. So there's a transfer of heat from the ocean to the atmosphere because of evaporation. Also, there's less sunlight getting into the ocean. And so that sunlight is being blocked by these clouds, and some of that solar energy is staying in the atmosphere. So you get the rise in global temperatures with El Nino. And by the same token, with La Nina, the skies are clearer over the tropical Pacific. More sunlight is absorbed in the ocean. There's less evaporation and less rainfall. And so there's less condensation heating of the atmosphere. And so during La Nina, global temperatures fall. And so you look here at this peak. This is 2015 and 16. That's the big 2015-16 El Nino. So you will see sometimes headlines like this. 2016 is the hottest year ever recorded, and scientists say human activity is to blame. That's because of the rise in greenhouse gases. But you see, they also note El Nino was a factor this year. This is a headline from early 2017. That's because El Nino is giving a boost to global climate, global atmospheric temperatures through anomalous heat loss across the air-sea interface. So then it's easy to understand why 2016 was the warmest year on record. And if you follow the logic, you can also understand this headline. NASA says 2020 was tied for the hottest year on record. Why wasn't 2020 warmer? I mean, there's been more greenhouse gases accumulating in the atmosphere over the 4 years between the 2015-16 El Nino and 2020. If it was just greenhouse gases, you would expect 2020 to be warmer. Well, this was the beginning of our 3-year La Nina. So there's more heat going into the ocean from the atmosphere. It's tamping down the rise in global mean surface temperatures. And so even though there are more greenhouse gases in the atmosphere, it wasn't clearly the warmest year on record. Now, understanding this gives you some clues into what has been called the hiatus or the slowdown or the pause in global warming that occurred at the beginning of the 21st century. This was where you see temperatures in the atmosphere were rising pretty steadily, and then they slowed down from 2000 to about 2013. And climate change deniers made hay with this. They said, ha, your model's all wrong. The world's not going to heat up that fast. We don't have to worry. But if you understand what we've been talking about, how ENSO affects climate change detection, you can see that this period of the slowdown corresponded to a period in which the La Niñas were strong and frequent and long, and the El Niños were weak and relatively infrequent. And so there was, over this decade-long period, there was a net increase in the uptake of heat by the ocean. The ocean is absorbing it like a sponge during this period and storing it in the deeper parts of the water column. Well, that hiatus came to a very abrupt end with the major 2015-16 El Nino. Now, since that 2015-16 El Nino, we had one very weak El Nino, and we've had a lot of cold. And global mean temperatures in the atmosphere have again plateaued, maybe even gone down a little bit. This is again a pause in the rise in global mean surface air temperatures because of the prevalence of La Nina conditions over the past several years. Now, if you look closely at this record, the final point, March of 2023, this is 1.24 degrees Celsius or 2.2 degrees Fahrenheit above the 20th century average. This is one of the highest air temperatures, global mean surface temperatures ever measured. It's the second highest March. The highest March occurred during this major El Nino. The second highest March has occurred during neutral conditions. The La Nina is over. The temperatures in the tropical Pacific are near average now, but we've got this near record March 2023 value. And that's because greenhouse gases have been accumulating in the atmosphere over the past 7 years since the last high March value during this major El Nino. Now we're getting a high value with no anomalous tropical Pacific conditions at all. Okay, so looking ahead, what's going to happen in the tropical Pacific? Well, we just come out of a 3-year La Nina. El Ninos typically happen once every about 4 years, so we're kind of due. There are about 20 groups worldwide that routinely predict El Nino La Nina conditions in the tropical Pacific, in particular the Niño 3.4 index shown here. And this organization, the International Research Institute for Climate and Society, compiles all the forecasts from these different institutions and puts them on a common format so we can see them. And what they're predicting is, if you start out with February 2020 to 2023 conditions, which are a little bit cold, that's the tail end of the La Nina, and you forecast March, April, May, June, May, June, July, August. So we're forecasting seasonal values marching forward 1 month in advance through 2023. A forecast below this line is for La Nina. Below the gray zone, which is the neutral zone, plus minus ½ degree Celsius. A forecast below this line is for La Nina. Above this line is for El Nino. Many of these models are predicting that an El Nino will develop, El Nino conditions will develop in the May to July period of this year with about a 60% chance. And that it will further develop and remain in place through the end of this calendar year. This is the most recent ENSO advisory issued by NOAA just a few days ago. And the 60% probability is shown here. Again, we're now in February, March, April, neutral conditions, but then a growing probability up to 60% probability by the end of the calendar year for an El Nino. So what does that mean for global mean surface temperatures? It means we're probably going to set new records in the near term if this El Nino really develops. And it's again, because for the last several years, the global mean surface temperatures have been tamped down by the cold conditions. And now the ocean is going to give a boost to the rising temperatures that are fundamentally due to the increases in greenhouse gas concentrations, but temporarily get these boosts because of ENSO. So let me conclude with a summary, and then there's time for questions if you're interested. ENSO is the strongest year-to-year climate fluctuation on the planet. Whether and how it is changing now and in the future is one of the most urgent problems in Earth system science because it has such broad impacts around the world. The instrumental record is too short to determine whether climate change has already affected the ENSO cycle in terms of its property and dynamics, but there are hints in the paleo record that maybe the last 50 years were more energetic, although there's a lot of uncertainty. So we really kind of have big question marks here. The model suggests that ENSO may become stronger in the future by the end of the 21st century by 10 to 20% because the increased ocean atmosphere coupling and efficiency of upwelling. There's a caveat here as well. It depends on the consensus of the current generation of climate models being correct that the background conditions in the tropical Pacific will warm up, which is different than the observed trend that we are seeing over the past 30 or 40 years. Climate change related warming trends are amplifying impacts of ENSO even today, even if we can't say with confidence how its properties and dynamics may change in the future. We can see the impacts of ENSO getting juiced basically by the underlying warming trends due to rising greenhouse gases. And finally, there's a lot of year-to-year variability in global mean surface temperatures due to ENSO. El Nino temporarily boosts and La Nina tamps down rising global temperatures. And with the forecast for an El Nino for later this year, and the likelihood that there will be one, given that the recurrence rate is typically about 4 years, and the last one was 4 years ago, you can expect that we'll be setting new global temperature records in the very near future. And with that, I will conclude, and thank you. And I'm happy to take any questions.
Thank you so much, Dr. McPhaden. I'd like to open it up to anybody in the Zoom room or in either of the classrooms streaming to ask any questions. Yeah, so Logan's asking whether the recent La Niñas, what effect those have had on the atmospheric rivers we've been having in Northern California.
That's a great question. That's a problem we don't have a real clear understanding of at this point. People are looking at it. Those rivers have really had a dramatic impact. And in fact, they were somewhat counter to what we might have expected during a La Nina. The previous 2 years, the previous 2 winters were really extreme drought. This past winter was off the charts in terms of rainfall because of the atmospheric rivers. That was not a La Nina effect or an El Nino effect. And I should say that, and it's a good thing you asked this question, is that El Nino and La Nina tip the odds for a certain kind of weather pattern to exist. It doesn't guarantee that it will exist. So even though often the desert Southwest experience severe drought during La Nina conditions, it's not a guarantee because there's a lot of other things going on in the climate system that can produce things like these atmospheric rivers that have nothing to do whatsoever with ENSO.
Thank you.
At least at face value. Thank you. Thank you for that question.
Dr. McPhaden, can you provide any insight into why the Eastern Pacific has been so cold this winter during a La Nina?
Yeah, that's because, excuse me, the upwelling is a big process in the ENSO cycle. If you have more extreme upwelling, more extreme trade winds, stronger trade winds, you'll have stronger upwelling. And that's basically the simple answer. But the system tends to reinforce itself because cold water in the east leads to higher pressure there. The higher pressure leads to stronger trade winds. The stronger trade winds lead to stronger upwelling, which leads to colder temperature and higher pressure. So this is the positive feedback. It's a positive feedback or a self-reinforcing feedback that makes the ENSO cycle work. Once you initiate these feedbacks, it tends to stay in, from several seasons in a particular state. And there's some very slow operating negative feedbacks that eventually switch the sign, but they take a long time to work.
I have a question for you, Dr. McFadden.
Okay.
So between the fourth IPCC assessment and the sixth, maybe I missed this, but what exactly changed?
Yes.
Did our models improve, and how did they improve? What new information did we have?
Right. Some models are at increased resolution. That is, their grid, their grid is smaller. That means there are fewer things that they have to estimate through recipes that are very crude. So improving the grid resolution is always something that modelers are trying to do, because that means you can more explicitly represent processes that are important. But it comes at a cost. You're talking about a three-dimensional system, and if you double the resolution, you're talking about 8 times the computing power required. So improving resolution is one. Another one is improving parameterizations, or these recipes. How, if you can't really resolve the cloud, what kind of a formula do you put in place that characterizes the formation of clouds? And a lot of people have looked at how to improve those formulas to estimate cloud formation on subgrid scale, that is in between the grid points. So I would say that we call this model physics. So model resolution, model physics are 2 important ways in which modelers are improving their models.
How quickly do you think that artificial intelligence will be able to catch up with, or the climate scientists will be able to sync up with artificial intelligence to then lead these models to being even more fine resolution?
Yeah, that's a great question. I mean, this artificial intelligence is now a booming industry, and not just in climate science, but in all kinds of areas of human endeavor, economics and all kinds of things. And so there is a growing use of artificial intelligence in trying to improve forecast models for both weather and climate, seasonal climate forecasting, but also in what we call projections. These are the century-long projections, looking at 100 years in advance. And I think there's still a lot of sorting out in terms of exactly what those contributions will be, because there's so many different techniques and so many different new problem areas to look at. But I would say I don't have a simple answer to this question, but I would say that the community is on this. And in 10 years from now, we'll have much more to say positively about what contributions artificial intelligence is making, not just to the projections and predictions, but our ability to analyze data and ferret out new kinds of patterns that we might not have otherwise seen through these artificial intelligence or deep learning techniques.
Thank you. Our students are in the early stages of their higher education, and things are changing rapidly. The climate's changing, technology is changing. What advice or wisdom can you give them as they are progressing through their academic journey and their career journey? And we've got, both Allison and I have non-majors and major students in our classes. So some folks are going into the environmental and geologic sciences and earth sciences, and others are not. So it's a broad question, but what wisdom or advice can you give? Thank you.
That's a great question. I got a degree in physics many years ago, and I realized that I didn't want to pursue a degree in physics, traditional physics. I wanted to do something that I felt made a difference to society, that would make the Earth a better place to live and work in. And so I turned to environmental science, and I really didn't have a good idea about what it was I wanted to do. I didn't have a specific idea. I got into the study of El Nino early on, and it was like a dream. Now, I'm not saying everybody should go into the study of El Nino, but I would say, get excited, get passionate about some problem, read about it, learn about it, talk to people about it, and then, follow that dream. There's so much to do in terms of understanding the environment and in, addressing problems like pollution and, climate change, biodiversity. I mean, there's just all kinds of really, really interesting and fundamental problems that are exciting to learn about, that are satisfying when you make progress, and you can feel good when you've unearthed some small piece of wisdom that makes the world a better place to live.
Thank you. Great advice. Follow what gives you that spark, because if you're following what someone says you should do and not what gives you that spark, you're going to burn out.
You got to be motivated from within, and you're not going to be motivated if somebody's telling you what to do. Find that spark from within and run with it.
We have a question in the chat asking, do you have any suggestions for people who are interested in following environmental justice?
That's one of those new areas, one of those emerging areas, and it's so great to see this. I mean, that would be a really exciting area to get involved in. I myself do not have much of a history of involvement in that. I'm just learning about it too. So I think it's, finding those individuals who are professionally pursuing this and, talk to them, ask them questions, maybe seek them out as a mentor, get their advice. I mean, this is a great area of study that links, what we learn about the physical world to, how we behave and treat one another as human beings.
So thank you very much, Allison, for having this idea. And thank you very much, Dr. McPhaden, for spending time with us today and helping us better understand El Nino and the impacts that it's going to have on our future, impacts it's had on our past. And we really appreciate your time. Thank you.
Thank you very much. I appreciate the opportunity.
Thank you so much, Dr. McPhaden. Take care.
You too.